Now let's talk about the closed interval method. Um, what we had with extreme value theorem, it was explaining to us if f is continuous and the interval is closed, then f has over that interval has a maximum value f of c and a minimum value f of d at some c and d within that interval. So this gives us some idea. And with the pictures that we watched, we realized that either f has a if at the end point the maximum and minimum is achieved, or within. If it's within, then it has to be a local max and min. If it's at the end points, then we can figure that out separately. And so there is a method of systematically finding absolute min and absolute max, which is really important for modeling. So the method is called the closed interval method. You have to have the conditions in the extreme value theorem satisfied. That is, f has to be continuous, and and the interval of the domain has to be closed. And then so you do this process. First, you find the critical numbers in A and B. So you find the critical numbers, then you evaluate f at those critical numbers. Then you evaluate f at the endpoints, namely A and B here. Then you compare whichever is the biggest is the absolute max, whichever is the smallest is the absolute min. So for example, let's find the absolute extrema of this function. Let's remember to find the absolute on the closed interval 0 and 6. Let's remember to find the absolute extrema on a closed set, we're going to use the closed interval method. Closed interval method, find the critical numbers, because the absolute min or absolute max could be a local min or max, or they could be end point values. And so first you have to find the critical numbers. Critical numbers can be found by taking the derivative and setting it equal to 0, or finding where derivative does not exist, both of those. And so now take the derivative. When you take the derivative in here, 2x to the third minus 15x squared plus 24x plus 6, this one becomes 6. The derivative of first term is going to be 6x squared. Derivative of second term is negative 30x. Third term is 24, and 0 for the last term. And then you can, you want to set this equal to 0. So as usual, the best method is to factor everything. And when you factor everything, then you can find the zeros of the f prime. So now that we factored, we see that there are at x equal to 1 and x equal to 4, f prime is going to be 0. And that means that the x equal to 1 and x equal to 4 are the critical numbers of f. And looking at this interval, both this one and this one belong to that interval. They're within that interval. So best way is to check the value of f. How do I do that? I write f of 1 equal to 1 to power 3 minus 15 1 to power 2 plus 24 1 plus 7, and I compute that. And then I find f of 4, which is 2 times 4 to power 3 minus 15 times 4 to power 2 plus 24 4 plus 7. And then f of 1 is going to be 18, f of 4 is going to be negative 9, and those are the two values that I evaluated. What is left? I found the critical numbers. I found the function at those two critical numbers. Now I have to look at the endpoints. So I have to plug in 0 in the function and 6 in that function and compare. F of 0 obviously is going to be equal to 7. And so that is not going to be any of the, so we check the endpoints. This one is going to be 7. If I plug in 6 in here, I get 43. Now, comparing all these values, the smallest value I get is -9. The highest value I get is 43. So basically, the absolute maximum is -9, and the absolute maximum, I'm sorry, absolute minimum, absolute min is -9, and the point is 4 and -9. Absolute max, is 43, and the point is 6 and 43. And now we compared the values, we found these, and let's see how it sits on the function. So this is the function, if you graph it, and if I look at the interval 0, that's 0, and 6, I see that this endpoint is the highest value, which is 6 and 43, and the lowest value is reached over here, which is 4 and -9. And so we're working within a frame, and it gives you the absolute min and absolute max. And you see this one is neither and this one is neither. That one's a local max, but it's not absolute extremum at all, and this endpoint doesn't give you any absolute extremum. We're continuing with section 4.2, and let's do a few iClickers. This one is iClicker question 3a of 4.2. Suppose that f is continuous on the closed interval a and b. Is the following statement true or false? The function f must have at least one local minimum and at least one local maximum on a and b, but not necessarily an absolute maximum or absolute minimum. I suggest pausing and thinking and coming back. So now that you paused, let's look at this. F is continuous and the interval is closed. Therefore, there should be an absolute min and absolute max. So the statement is false. Now let's go to iClicker question 3b. Suppose that f is continuous on the closed interval a and b. Is the following statement true or false? Remember, again, this is the when you have continuity and you have a closed interval, you can use the extremum theorem. And extremum theorem says that f has an absolute min and absolute max. And this is exactly that. It says f of x is between m and m for some values, m and m. These are different values. So you can pause and think, and the answer is true. iClicker question 3c of 4.2. Suppose that f is continuous on closed interval a and b. Is the following statement true or false? Every absolute maximum or minimum must occur at either one of the endpoints of the interval or at some x value in the domain where f prime of x equal to 0. And let's pause. The answer, let's see. So we're looking for either endpoints. This is again extreme value value theorem. And value. And for extreme value theorem, the absolute max and min is happening either at endpoints or at or critical points. And what is critical points? So this one says either endpoints or f prime when points that f prime of x equal to 0. But critical points could be f prime of x does not exist. So this is a false statement.